Well, thank you very much, Ben. It's fantastic being here. It's a big honor to be invited, and I must obviously thank you, Ben, for actually organizing this. I really didn't know about this extremely cool event until Isaiah gave his presentation a few weeks ago, and it's really great to be on air here. So thank you very much. Thank you for doing this. You and I talked a little bit, and obviously this is all a little bit COVID inspired, but I really hope that this goes on even once we are done with the malady. I really wasn't really sure what I would like to talk to you about. I want to talk to you about the research we do um, in my group, and maybe really the best way to describe our research is it is all about solids. It's all about doing chemistry in the solid state, and you can kind of see where this comes from by looking at the background where I come from. So I'm originally from Croatia. This is where I did my undergraduate, focusing on really X-ray diffraction and determining structures of solids using crystallography, and really figuring out what are the structures of molecules in the solid state. And this was great fun, really exciting, except at some point, while you have seen a number of crystal structures, you start to get a little bit tired. There is only a certain number of times you see a benzene or a naphthalene ring in a molecule, and you get excited about it. So I then went on to do a PhD with Len McGillivray at the University of Iowa, which was absolutely a great time and a great place. And Len introduced me to something else. You can actually do not only measurement of structures and molecules in solids, you can actually use solids to conduct chemical reactions. And what we did with Len was really shine light, visible or ultraviolet, UV, on crystals in which molecules were arranged in a certain way, and you would get a chemical reaction, a dimerization taking place. And that was absolutely fantastic. But you know what? After a few years of doing that, there is only a certain number of dimers you get excited about. After all, making dimers is a reaction. You take the molecule A, and you take another copy of molecule A, and you make 2A. So there is really something about solid state chemistry at that point that was saying you really cannot get all that richness of chemistry, of synthesis that really turns people like me on in the solid state. You must work in solutions. And that all kind of changed in my head when I went on to do my postdoc with Bill Jones at the University of Cambridge, working on pharmaceutical materials, where I discovered this area of solid state reactivity called mechanochemistry, chemical reactions that happen under mechanical force, like grinding or milling. And it turned out that, while I was looking at making complexes of molecules by grinding them together, it became obvious that you can actually use this method to do a range of other types of chemical reactions. And this is really what we've been doing in Canada since 2011 at McGill. We have been trying to show how you can use this grinding chemistry to do not only, dimerization reactions, but actually create all these synthetic freedoms that chemists are used to in solution, in liquid media, create them in the solid state. And this is actually quite important from the aspect of what really is I think on everybody's mind these days, and that's being environmentally friendly, conducting chemistry in a safer way, in a cleaner way, essentially the idea of green chemistry. And this way of performing chemical reactions in the solid state is really very much aligned with the ideas of this greener, more sustainable chemistry. And that's also what I'll try to talk about. So one thing I need to warn you, and I guess I should have really warned Ben first, is, you never know who you invite, so, this may be just a complete disaster. So, but I hope not. I hope it's going to be fun and interesting. And you know, before I start, I need to obviously thank the people who do pretty much all the work. And that's my research group and our collaborators. And here is some of the people that whose work I'll be presenting. It's a really gifted, really talented, and overall really wonderful group of undergraduates and graduate students, PhD, masters, postdocs, visiting profs. We have a bunch of very different people at all stages, from very different backgrounds, from different countries. And that really makes us, I think, more dynamic, richer, and more excited about things we do. We combine a lot of different ideas from different origins. So let's maybe, instead of talking about green chemistry, ask a very fundamental question. You know, those are the best, the very simple ones, like what is chemistry? And you know, to answer that question, I'm going to try to answer it not as a, well, not as the very first full professor of chemistry giving a talk at this event, but I'm going to try to answer that, you know, from a maybe from a maybe a somewhat less experienced level. So what is chemistry? Well, most people, if you ask them what is chemistry, they kind of remember it was a horrible subject they had to take in school or the undergraduate, and it's all about formulas. There is some chemical reactions, but it's all about formulas. So for many people, chemistry is something like A reactant plus B reactant gives us a product C, or C and D. And really, in this equation, the chemical formula, right? The chemistry is really contained in here, in this one little arrow that really illustrates all the wealth of chemical transformations that have been developed over the last few hundred years. So this is how people usually think about chemistry, but we know chemistry is not equations. Chemistry is not necessarily what's written in the books. For people like me, chemistry is the stuff you do in the lab. I occasionally still like to go in the lab and do stuff. I usually make a mess and then the students ask me to leave, but you know, whatever. Anyway, so this is chemistry, right? If it was A plus B gives you C, that means you would take your reactant A or B, shown here, and then mix them together, then you get C. Is that how chemistry works? We all know that it's really not. I would say, I'm going to be liberal and say in almost all chemistry curricula out there, the way teaching of chemistry is done, experimental chemistry, it goes along the ways. Take A, you put it in a solvent because chemistry must be done in solvents. So you dissolve your A in a 10, 100, sometimes 1,000 times larger amount of a liquid, a solvent. And then after you have dissolved your A and B into these clear solutions, you mix them, and then from A and B in solution, you make product C. And this product C, you need to somehow remove, isolate from your system. Maybe it precipitates out so you can filter it, maybe you distill it away, and so on and so forth. I think when one thinks a little bit more about how chemistry practically works, it's very obvious that even for simplest reactions, this A plus B gives you C is a vast oversimplification. Now, the use of solvents is very convenient in the lab, but also already in research labs, in teaching, not to mention industrial scales, using solvents is an issue. And it's an issue because most of these solvents used are typically organic liquids, which very often tend to be flammable or volatile or in some other way hazardous to health, cancerogenic or teratogens. You name it, that's probably what they are. People also look for solvents these days that are cleaner and safer. For example, water may be the best solvent, but you know, in a world in which supplies of drinking water are kind of dwindling, maybe using water to conduct chemical reactions as a solvent is not ideal. So really, especially at the large scale, the use of solvents is a problem because all of these solvents, after chemistry is done, need to go somewhere. You either recycle them or you dispose them in some way, and neither of these solutions is really environmentally friendly. In the lab, in a research lab, one can dispose of small amounts of solvents, but at a large industrial manufacturing scales, whether the solvent is I don't know, ethanol, or whether it is toluene, or whether it's aqueous hydrochloric acid. This solvent needs to somehow be removed, recycled, and that, if nothing else, causes a lot of energy consumption, a lot of cost, and so on. So at this point, you can say, well, this guy is giving us this presentation here, and he's kind of exaggerating things. So, you know, you don't need to believe me. So you can ask other people what they think about what chemistry is. And, you know, people listening to this right now, you may be physicists, you may be chemists, maybe you have finished undergraduate degrees or higher in science, and you think this is funny. But believe me, your friends, your family, your neighbors who have not finished science degrees are probably very likely to see you as a chemist as somebody like this. So obviously I nicked this image from the internet, and I just want to highlight this general idea of a chemist as somebody who not only has this frizzy hair and glaring eyes, but also somebody who works a lot with what? With solvents. Look at these flasks, solvents, fuming liquids. Hollywood B movies love that, right? So it looks like this idea of using solvents is not only heavily ingrained in chemistry itself, although they're problematic, it's also really a part of the cultural perception of what chemistry is, what is a chemist. Now you can say, again, this guy is exaggerating. So you know what? You don't need to believe me. Why don't you simply ask the world's largest source of information, Wikipedia? So I asked Wikipedia, what is chemistry? And this is the result I got. I've done this a few years ago. I don't think it changed much. So, you know, don't bother reading the text. Check out the picture. The picture is worth 1,000 words. Chemistry is all about flasks and solvents. That's really what the simplest answer to the question, what is chemistry, is. Okay, so we kind of now established what is chemistry. Chemistry is really cool, fun, and great. Depends on solvents, which are very, very often toxic, and we need to do something with them. So I'm going to ask now another fundamental question. Why? Why do we need to use these solvents? And the reason I'm asking why is because if you think about how people present past cultures, past civilizations, there was a lot of chemistry, material science happening without solvents. I don't know, this person here, is making an object, making a material, maybe making fire, causing a chemical reaction, definitely not by using solvents. And there are many ancient cultures, medicine has been strongly attached to using solid state roots to make medicines. Here you see all of these mortars and pestles, and actually, if you take a walk through a busy street in London, UK, probably over every pharmacy you're going to see this symbol of the pharmacist, which is a mortar and pestle being used to make pharmaceutical derivatives. So this is what we call mechanochemistry, chemistry induced by mechanical action, by grinding. For a long time, this used to be called mechanochemistry, but since few years ago, Tim Hanusa and his fantastic group at Vanderbilt have actually decided to also call it MChem, which I think is absolutely cool. But anyway, this mechanochemistry has been with us for a while, and you can say, oh my God, this guy is really, really exaggerating. First, he tells us about this, and then he talks about Wikipedia, and now he's showing us these pictures he nicked off the internet and promoting some kind of story of solid state chemistry. Tomislav, can you give us a reference? So here is actually a reference. So a really good reference on the early uses of solid state chemistry comes from Theophrastus of Eresos, a Greek philosopher from roughly 2,500 years ago, who succeeded Aristotle in his school of philosophy. And among the other books that Theophrastus wrote, there is the one called On Stones. And actually, if you go on the website, I think of the Ohio State University Library, you can download for free a PDF version of this book in the original Greek text, the English translation, and also in Latin, in case you're into such things. Anyway, so what this book is really, it really has been a summary of all sorts of, let's call them processes that Theophrastus could learn about in his ancient world about making metals, processing minerals, and so on. And in a way, obviously, chemistry was not around then as a firm science. But in a way, this book is one of the earliest, if not the earliest, I would say, textbooks of inorganic chemistry. Anyway, so check it out. It's not too difficult to read, and it has some really fantastic examples of solid state chemistry. And this one is my favorite. This is actually a method to make mercury. And I was first really kind of driven to look into this by the late Professor Laszlo Takacs at the University of Maryland, who was a physicist and a big aficionado of mechanochemistry. And he actually dug up this example of method to make mercury in the ancient times. Mercury used to be a very important metal. Today, we don't want to use it because it's nasty stuff. Well, occasionally we use it. I'll talk about it later on. And the way it's actually made these days is made from a mineral, mercury sulfide, known as cinnabarite. And the issue with that material is that it's so insoluble, extremely poorly soluble, that the only way we can dissolve it to actually get mercury out is by using really, really nasty chemicals like nitric acid, hydrochloric acid, and so on. So this whole idea of obtaining mercury from its mineral is terribly challenged by the fact that the mineral is extremely poorly soluble. However, there comes this paper from 2,500 years ago on stones that actually describes you can simply take mercury sulfide, cinnabarite, as they called it, right? And you can grind it in a mortar with a pestle made of copper or bronze. And somehow, magically, if you perform this grinding, liquid mercury comes out. And Professor Takacs actually was the person who looked again at this chemistry after 2,500 years ago and said, wow, this actually really works. And what this really is in the language of modern chemistry, this is a, excuse me, a galvanic reaction between mercury sulfide and solid copper of the actual mortar and pestle, which leads to a redox process where mercury is reduced to mercury zero, liquid, and copper is oxidized to different sulfide forms. But again, I don't want to spend too much time on this, but I still believe this is one of the most inspiring examples of what can be done using solid state chemistry by really removing ourselves from the need to dissolve and to use solvents. By trying to do chemistry in the solid state, suddenly we are doing chemistry that previously was not considered possible. And at the same time, we are eliminating the need for really, really very aggressive reagents and solvents. And I think that's great. Now, a little bit more about mechanochemistry. People these days look at mechanochemistry and they say, wow, that sounds really cool. You know, one of those cool buzzwords. Well, the name mechanochemistry appears to have been around for over 100 years. It was introduced by the German physical chemist Wilhelm Ostwald while he was trying to organize the chemical science based on ways in which you bring energy to the reaction. So Ostwald was thinking about the following lines. You know, I can induce chemical reactions by bringing heat, light, mechanical energy. I'm going to call this thermochemistry, photochemistry, radiochemistry. I'm going to call that mechanochemistry. So that's kind of where it came up with. And if you really want to know a bit more, well, obviously I'm kind of pushing our own little paper here, but a really nice review that has, I think, 15 or 16 authors from all different disciplines of chemistry was published roughly 8 years ago. And I you know, it's a bit old now, but I still warmly recommend it. It's a really nice joint work where everybody tried to say, wow, mechanochemistry means this and enables that in my field. So check it out if you want to learn more. For us in my group, mechanochemistry is something we are investigated as a reaction environment. And it gives us benefits such as allowing us greener, solvent-free chemistry. At the same time, this greener chemistry, this different reaction medium, which is the solid state, enables us sometimes to make reactions simpler, avoid some reagents, actually discover new reactions, maybe discover new reagents, and so on and so forth. So it's a really rich area, and you can definitely spend, I think, several lifetimes doing mechanochemistry, and it's fun at the same time. So again, pushing shamelessly around papers. If you want to know more about this idea of chemistry as what we think about as a different cleaner, solvent-free system of chemical synthesis. I'm playing a little bit of tunes here, right, on John Dalton and his new system of chemistry. Sorry about that. But if you want to know more about that, there is a review that was published by one of our students a few years ago, Jean-Louis Daw, and we are trying to summarize some of these ideas. Check it out if you're interested. In a nutshell, what we are trying to do, we are trying to make exciting new materials and molecules, but we don't want to make them from commercial chemicals that you get from companies such as, I don't know, Sigma Aldrich, which I like to think about them as the Walmart of chemists. Yeah, you go there and buy this and that. We actually want to do green chemistry, cleaner synthesis of these new exciting materials, not from bench chemicals. We want to see how we can use very basic starting materials, minerals, rocks, biomass to actually go there. And in order to do that, the biggest obstacle, I would dare say, is the fact that these materials, the very starting precursors which we depend on, well, they're accessible to us because they're so stable, they're insoluble, they're essentially rocks. So what you're trying to do here is find out how we can take these rocks and actually convert them in a cleaner, safer way into exciting new materials. And obviously want to do that without solvents. So what do we do after all? Here is a video that was taken on an iPhone by a former visiting student, Michael Brandt, who is now, I think, actually doing a PhD in Liverpool. I hope I'm right on that. And when he was visiting our lab a few years ago, he actually had an iPhone with a fisheye lens and some kind of cool app, which old geezers like me don't really know much about. And he could actually record the motion of a machine we call a ball mill and slow it down, the recording, by 4 or 10 times. So what he did, he made this little movie of a mechanochemical reaction. The big white thing here, that's a ball. It's made of zirconia, very inert ceramic. The powder here is actually a mixture of a organic molecule, dibenzoyl methane, which, for those of you who don't know, it's a chelating molecule. It's sort of a solid version, if you wish, of the famous ACAC. And the dark spots here are actually particles of europium chloride. So what we want to do now is make a europium complex with this ligand by milling. So let's start shaking this left and right. That's called ball milling at a frequency left and right of 30 hertz. So this little jar moves back and forth 30 times a second. It's obviously slowed down a bit, but it's still quite fast, huh? Okay, hold on. Let's try to do this again. I really like this video. See how the ball starts to move, crushes the material, and then very quickly everything kind of turns orange. And you know what? Within a minute or two, really, the reaction is done. And I like to show this video just to illustrate how these solid state reactions can be very, very fast. And that's one important thing. So reactions in the solid state, especially if you push them around a bit by grinding, by ball milling, like here, can be really, really fast. They can be faster and simpler than solution chemistry. Okay, so this is kind of the sort of thing we do on the lab scale, a few hundred milligrams to a gram. There are obviously devices to scale up. But then, who cares about all this? I've been telling you about this mechanochemistry, solutions, but who really cares about this? I would say actually that a lot of people care. So this is something we published 4 years ago. It was an overview of all the molecules in pharmaceutical industry that have been modified through solid state mechanochemical techniques, which means that all of these molecules have somehow been modified. When I say modified, I mean people made salts or co-crystals or polymorphs and so on. And there was then already a very small subgroup of molecules shown here, which have actually been made mechanochemically. The actual molecular structure was synthesized in the solid state environment. And by now, led by a number of groups, this field of medicinal mechanochemistry has already generated, I think, 3 or 4 times this number of interesting drug molecules. So I really believe this is a terribly interesting opportunity for greener, safer manufacture of pharmaceuticals. Our little contribution to that was demonstrating a process to make these sulfonylureas by copper catalysis in a ball mill. And we just wanted to really see whether we can make these commercially previously not now relevant molecules like tolbutamide, chloropropamide, which are all antidiabetics. So this is done by former student David Tan, really fantastic young organic chemist. Excuse me. And this work that he did showed not only that he can do this chemistry in a cleaner way, but it's actually one step shorter than industrial processes. So that was cool. What was even cooler, I think, is we actually got in touch a few years ago with Evelina Colacina at the University of Montpellier in France, who took this chemistry and actually translated it into a teaching laboratory for undergraduates. And I was just stunned by the fact that, you know, suddenly you have a class of undergraduates in organic chemistry taking this research of making pharmaceuticals using green chemistry and doing it. And not only that they repeated the chemistry, they actually also were challenged by the task to scale it up a little bit using a different instrument, and it worked. So this is really cool, and I must say, you know, it's a pleasure to work with people who are not only interested to do green chemistry, but actually teach students to, as Evelina says, to think this chemistry differently. Anyway, check out this paper if you're interested. We also looked at this mechanochemistry in other ways. So with the former postdoc Vjeko Štrukil, who is now back in Croatia running his own research at the Institute Ruđer Bošković. This is some very simple chemistry we've done, coupling of isothiocyanates and amines or anilines to make thioureas. I really don't know why we made thioureas. I guess we were into thioureas then. But anyway, in this project, we used different methodologies to show that we can synthesize almost 60 different thiourea derivatives mechanochemically in complete conversion. And the best thing about this is once you made these molecules solvent-free, the powders you got, these are all solids, were microcrystalline, which means we could actually try and many times succeed to determine their structures, crystal structures. These are crystal structures, actual data from powder diffraction, which we could confirm by solid-state nuclear magnetic resonance, NMR, by solid-state reflected infrared. Anyway, what we're trying to show here is that we can not only make molecules solvent-free, we could then analyze them fully or almost fully solvent-free. So this is sort of a pet project we have, which is how do we develop strategies to perform a completely solvent-free laboratory research? I strongly believe it's possible. I know there must be obstacles, but you know, one needs to be a bit crazy and enthusiastic to make this happen. So it'd be wonderful if one day we could transform all of our chemistry in industry, in research, into the solid state. We are not the only ones. Some of the really, I would say, legends of mechanochemistry these days are people like James Mack, who does some fantastic catalysis and organic synthesis. I strongly encourage you to check out his papers. He's showing here, for example, how organic reactions can take different paths if you add a small amount of the liquid additive. So the reaction can selectively be directed by milling to catalytically give you either this diene or this enine product. Cool stuff. Or, for example, one of the, I think, legends of organic synthesis by mechanochemistry is the work by the Lamati group in Montpellier, who have shown what is still really a tour de force of mechanochemistry, the synthesis of this oligopeptide leuenkephalin by multi-step peptide bond formation, deprotection, solvent-free chemistry. So again, this is still one of the most complex molecules which were made step by step through the use of mechanochemistry and thermal chemistry. Now we have been involved in a bunch of different projects. So for example, we really have a very exciting collaboration with the group of Masad Dama at McGill, who are absolute experts in nucleotide chemistry. To make the long story short, we actually have developed methodology to make trimers, tetramers, and couple them further of DNA and RNA. So this is fantastic work by really talented students like James Thorpe and Dan Riley. And really, we have a methodology now where we can create and make DNA, RNA systems without having to use solvents, which I think is interesting not only in the context of manufacturing and green chemistry, but also in terms of philosophically, you know, if you can make DNA and RNA in the solid state, then why are we talking about things like the primordial soup? Maybe it was more like a primordial sandbox. Who knows? Anyway, We also have a really cool collaboration with the group of Professor Carino Claire here. And initially, this collaboration was led by this very dynamic postdoc, Fabian Hammerer, demonstrating we can actually use enzymes in the solid state. And our focus was actually on showing that you can use enzymes to mechanochemically, through a process called reactive aging, or raging, as Fabian called it. You can actually depolymerize biomass into monosaccharides very efficiently, very cleanly, without having to use solvents. Anyway, so check out these papers if you're interested in. Obviously, you feel free to ask questions. And I want to change topics here a little bit, and I want to talk to you about frameworks. And this particular framework here is a picture of the Buckminster Fuller Dome here in Montreal. If you ever visit Montreal, come check out the big original buckyball here. And the frameworks I want to talk about are metal organic frameworks. Those of you who have been following chemistry for the last couple of decades, you will know that MOFs, for friends, metal organic frameworks, are a really, really exciting area of modern materials. The idea that you can use metal ions as nodes and connect them by organic molecules as linkers to create these wonderful, aesthetically very pleasing nets that then can also be used in many ways for catalysis, gas storage. People say they want to put hydrogen in there and have a car being driven on hydrogen fuel and so on. MOFs are terribly exciting. And you know, when my group sees something that's very exciting like MOFs, we are interested in looking at them. They're obviously wonderful structures, but our primary concern is, wow, if you want to make this material that's going to save the world in 20, 30, 40 years, well, you do design, and we'll try to think about how do we make the synthesis simpler, cleaner, faster, and hopefully scalable. And mechanochemistry, I think, can help. Mechanochemistry of MOF synthesis is not something we invented. It was actually first introduced by a really, really well-respected group in the field, led by Stuart James at Queen's University in Belfast in the UK, who reported the first mechanosynthesis of a MOF material, I believe 2006. Check out, this really is the first paper. And our interest is not so much in making MOFs, but making MOFs from the simplest precursors, right? So remember, we want to take those rocks, carbonates, oxides, maybe even silicates or something, and turn them into metal organic frameworks. And here is an example of some chemistry we do. We developed a really, really simple process to make these Xylitic frameworks, these Xylitic imidazolate frameworks, ZIFs, which essentially mimic the structure of zeolites, which have a tetrahedral silicon or aluminum bridged by oxygen. They mimic this structure by taking a tetrahedral metal like zinc or copper or cobalt and so on. And instead of oxygen atoms to bridge them, they use these bigger organic ligands, imidazolates. So this is one very, very popular and very well-known family of MOFs, and we wanted to know how we can make them from a metal oxide, and the solution was extremely simple. You take this imidazole ligand, they tend to be cheap, readily accessible. You take some metal oxide, zinc oxide, trivial, you grind it together. Maybe you catalyze it a little bit with some protic salts, or maybe you add a trace of liquid to both kind of lubricate the reaction or to actually help organize the structure into a certain framework type. And it works beautifully. So here are some examples here. Don't worry about these powder diffraction patterns. Just check out the structures we can make. So it turns out that if we tweak the reaction conditions, we can selectively make frameworks that have different connectivities, different shapes, what in framework chemistry is called topology. And we can really control that. Well, everybody can control that if you use mechanochemistry by adding a certain liquid or performing milling for a given time and so on. And you know, this is something that excites us and other people. For example, with my colleague here, Gonzalo Cosa, who is an expert in luminescence spectroscopy, we actually have shown we can use this methodology not only to make these MOFs by grinding things together, but if you add in a small amount of a fluorescent dye, these boron dipyromethanes, BODIPs, you can actually trap this dye inside this framework as it's forming. And now you have this new generation, if you wish, of fluorescent materials. And it turns out you can actually put different dyes in there. So you have red and green and blue. And now we are looking at how do we actually get white light out of this. So a really fun collaboration, very colorful, but again, it shows how you can generate new, more complex systems through mechanochemistry. I cannot really go with this presentation without highlighting again one of the best ever students who stayed in our group last year, Isaiah Spate from Tim Hanusa's group at Vanderbilt, who was actually kind enough to work on mercury. And this was an example of really fun work that also explored mechanochemistry, not just to make MOFs, but to investigate MOFs with elements that are normally not explored. And we discovered some cool new things. But anyway, now I've shown you a ton of things, and you're probably getting really tired now. It's getting close to midnight in some places. So you want to say, how does this work, right? He just grinds this and that's it. And that's a fair question. And honestly, the answer to the question, how does this work, maybe 10 years ago, would have been mostly, you're not quite sure. Now also we are not quite sure, but we got exciting new tools. One of them is we actually managed to find out that you can actually take your ball milling device. Here is a ball mill, and you stick it in the path of a really high energy X-ray beam, for example, at the European Synchrotron Radiation Facility in Grenoble, or more often these days in the German synchrotron facility, DAISY, and you shoot X-rays straight through the ball mill reactor, through the jar, as it's shaking about, and you record movies that look like this. So this is a powder X-ray diffraction movie of a mechanochemical process. These three lines, that's zinc oxide. The little spots here are those imidazole molecules, they're microcrystalline. And when you look at the middle of the screen, you will see these new rings appearing. These new rings are the signature, the structural signature of the nascent, in this case, product metal organic framework. And this really was the very first movie, the very first real-time in situ observation of what is structurally happening chemically inside the ball mill. You may notice this ring that comes and goes here, gets lighter and darker. That ring is actually a diffraction signal from the ball that we are using to mill the sample. It's a diffraction line of steel, of iron. So what do we do now? Now we and a bunch of other groups, because this method really became very popular, there are at least 4 different synchrotron facilities in the world now that offer the possibility to do this. Now people can actually look at the mechanisms of what's going on. So here are some really early kinetic curves of how the reaction profile changes when you mill with the addition of a liquid or less liquid or more liquid. And in making these ZIFs, you can see that you take your metal oxide, you take your imidazole reactant, and when you mill them, you don't go straight to this framework which has a topology, the structure of quartz, QTZ, but actually it appears through a series of intermediate phases. So we are now starting to see these complex reaction mechanisms, and we are thinking about how does this work? Why do they form? And really the first question was, how do we explain this? Excuse me, we take one organic ligand and we combine it with zinc, and we get this sequence of structures forming. This one has a topology that's known as sodalite. This one was a brand new material previously never known, so we called it katzenite, after the postdoc who figured it out, Thanasis Katsenis, who is now back in Greece. And then here, diamondoid-like framework. But if we have a slightly different organic linker, we replace a methyl group on it with a ethyl group. We again get multiple steps in the reaction, but now frameworks look completely different. This one has a structure which is known as zeolite rho. This one has a topology of analcime. This one quartz. So why does this happen in the first place? Are these some kind of strange high energy phases we are making? Are we making new chemistry, or is this something we would expect? And this is where we're lucky enough to actually join forces. By the way, I think you will notice a lot of things we do are always in collaboration, because, you know, when you meet new people who know different things, do different things, you can actually move your science, you can move things forward much more quickly and do more. So we were very lucky to actually work with Alex Nabrodsky, currently at Arizona State University, who is an expert in experimental thermodynamics. And working with them, it turned out that the reaction sequences which we are seeing here in MOF synthesis are actually perfectly consistent with thermodynamics. So we start with a product which is higher in energy, and then the next one, intermediate, is lower, and then lowest, and so on. So this may sound trivial, but I think it's important to stress, because often mechanochemistry is, people think of it as magic and so on. It's not magic. Everything really is thermodynamics. There is nothing terribly unusual here. We just need to come in and measure. Now, measuring these stabilities also got us in touch with a postdoc then, and now running his own research group in Poland, Michalis Archangelskis and Andrew Morris in Birmingham, who actually introduced our group to periodic density function theory calculations. And the nice result was that actually all what these straight lines are showing here, to put it in a nutshell, they're showing that we can calculate the stability of MOFs and find out that the calculated numbers are really well correlated. They correspond very well to the measured values, which we obtained with the help of the Nawrotsky group. So now we know that we can actually calculate the stability of MOFs and measure it very well, which then makes you think, can you now start to predict MOF structures? So now we are not talking about mechanochemistry anymore, but about understanding the energetics of MOFs. And the latest contribution to that, I need to highlight here, came from the collaboration led by the student James Darby with Andrew Morris and Michalis, demonstrating the first method to actually do completely ab initio, from first principles, prediction of crystal structures of MOFs. So now what we are looking at is how we can actually predict the stability of different MOF structures and then try to confirm these predictions using mechanochemistry as a really good synthetic method. So watch this space. This is, I think, pretty cool work. But now getting to that, we're talking about energy and stability of these metal organic frameworks. So how about the actual energy content of a MOF material? For example, you have a MOF, people want to use these metal organic materials for a number of things, sometimes for high temperature reactions, high temperature separations. How stable are they? Are they flammable? How much energy will be released if a MOF goes on fire? I would say these are also some technologically interesting questions. So this is what we tried to do. We took a number of MOF designs based on different molecules, some of them commercial, some of them we kind of made. And we did bomb calorimetry. So we simply put them in a calorimeter, oxidize them, and measure the energy enthalpy released. And turns out, interestingly, if you express this energy in terms of energy density, so energy released per volume of the material, or specific energy, so energy released per weight of the material, that the energy is released on combustion of MOFs. Here are carboxylate MOFs in green. Here are these ZIFs in red. Some of these energy densities are definitely exceeding those of TNT, hydrazine fuels used for rocket propulsion and satellite maneuvering. Some of them are exceeding in energy density kerosene, and so what we thought about was like, wow, these normal MOF materials are actually loaded with energy, and so maybe we should be careful. Maybe you don't want to set these on fire or something. So we kind of got interested in how do we set MOFs on fire? Are they flammable? And this is what the postdoc in our group, Hatem, tried to do. Here is a sample of this popular framework, ZIF-8 so-called. You can buy it from a number of companies. It's been around now for a while. And let's see if we can set it on fire. Hold on. This is the fun part of the presentation, okay? Let's take a blowtorch. Okay, here's a blowtorch. And that was a bit disappointing, honestly, because we thought we're going to publish a paper about, how one needs to be very careful with MOFs because they're flammable. It's going to be a big paper. But no, actually, this thing is not flammable at all. It just carbonizes, terribly boring. But maybe our geometry is wrong. Maybe we need to expose it more to air. So here we have ZIF-8 again, the MOF. And we have it here on a set of Kim wipes. And let's just set that on fire, see what happens. Okay, set the Kim wipes on fire. Go Kim wipes. And well, check this out, right? ZIF-8 doesn't care, the paper burns and the ZIF kind of like, smolders a bit and then kind of chills. So yeah, it looks like, yeah, these are definitely energy rich but kinetically stable materials. So farewell to your paper about MOF flammability, right? Well, the idea kind of lingered, how could we potentially ignite these MOFs? How could we potentially take these materials, which we can design in different ways, and ignite them and maybe start to develop them into a different type of fuel for maybe different, maybe cleaner, maybe more efficient propellants. And this is where really, again, we were lucky enough to bump into our colleague, Robin Rogers, currently at the University of Alabama, who did a tremendous amount of work on ionic liquids, including some ionic liquids which are so-called hypergols. Hypergols are essentially materials which will spontaneously ignite when you put them in touch with an oxidant. So this is a fantastic property, this ignitability on touch with an oxidant. It's a great property for satellites and for essentially maneuvering in space, where you need a really good way to turn the fuel on and off. Objects such as International Space Station are being held up in space by occasionally burning hypergolic fuels for attitude correction. Anyway, so these hypergolic ionic liquids, to make the long story short, usually work by adding some unsaturated groups on the molecule central to the ionic liquid. And guess what? That molecule is often a imidazole or a imidazolium cation, shown here. And what we thought here, talking with Robin was well, this imidazolium cation, formally, if you look at the electron distributions, looks a little bit like the imidazole linker that you have in a MOF, in a ZIF, right? Both nitrogens are occupied with something, and so formally this ligand here is not really an imidazolate, it's really an imidazolium. So the idea was very simple: stick on a few unsaturated groups and see if you get a hypergolic behavior. And this is what we did. So here is an example of a hypergolic drop test, where you have an oxidant, in this case, I think a few microliters of concentrated, highly concentrated nitric acid. And here is a MOF, right? So let's see what happens. I'm going to start the video now. And this time it's really slow motion. So this is recorded at a rate of 1,000 frames per second. So this little droplet is falling down very slowly. And bam. So that was very, very different than those attempts to actually set those MOFs on fire using a blowtorch, right? So it turns out that this is a really good design. Let's do this again. I really like this video. So this is a really, really good design to make hypergolic MOFs, and you can actually apply to different types of components. There we go. And it turns out that, it's not only me who likes this video. Apparently, CNN also liked it a lot, and they gave this the best ever title, ZIF Pole Bang. So anyway, check out this if you're interested. The Hatem's video of this drop test is shown here. But what we have now is actually families of different MOFs that can be ignited, and they can be ignited very quickly. Important property here is the so-called ignition delay. And here with the little star, we indicated the times from each video. When does the material first catch fire? And you can see that these ignition delays are measured in milliseconds, 2, 5. We actually have materials that actually ignite in less than 1 millisecond, which is not only sufficient, it's definitely fantastic for apparently for aerospace propulsion. Now, what do we want to do with this eventually? We would like to develop these MOFs into, I like to think of them as new tunable fuels that maybe one can use to actually replace what's currently being used in aerospace industry. Why is this man or a woman wearing the space outfit? That's not an astronaut. That's the person who's actually fueling a satellite or a rocket with the currently used hypergols, such as hydrazine. And hydrazine is not only flammable and volatile and all that stuff, it's actually also extremely cancerogenic. So actually one of the big impediments in further expanding the aerospace industry is also the high toxicity of these materials. So we are here looking at MOFs. If you wish, we started off with mechanochemistry. But this is for us a different perspective of green chemistry through the solid state. We want to use these solid materials to actually provide alternatives to make aerospace travel and space industry cleaner. And actually, one of our students, Christina Motillo here, she actually has taken this very seriously and started up a spin-off company that she's running right now. They got some really good funds to actually promote and develop these functional materials, MOFs, for aerospace propulsion. So with this, I'd like to thank you, and I hope I haven't bored you too much. Yeah, thanks a lot.
All right, thank you, Tomislav. Rest assured that was not boring. That was awesome. Uh, we in chat have been having a blast talking about the talk. So yeah, it's great.
Well, I'm glad you're having fun, and
Oh yeah,
that's why we are all here.
absolutely. All right, so we have a ton of questions. So I think I'm just going to go ahead and jump straight into them. First one here is from Isaiah, and he wants to know what your favorite form of mechanochemistry is.
What is my favorite form of mechanochemistry? Isaiah, you're putting me right on the spot. This is just not fair. Unbelievable. Look, I love all these flavors of mechanochemistry. And recently we started working on actually using acoustic vibrations as well to grind samples. So right now, that is my favorite form of mechanochemistry.
Okay. Okay. Now this is a question I had. So solid state is clearly the goal with this, where you pretty much eliminate all solvents from the reaction, or nearly all of them. But could you envision a case where a solvent could be used in the mechanochemistry reaction in such a way that you still end up with a solid? So the solvent itself actually participates in the reaction itself.
Right. So again, we want to do this in the solid state, but we are not also terribly orthodox that way. So occasionally we add a small amount of a liquid in this and that, and we call this liquid assisted grinding. Now, one thing, with this liquid assisted grinding, it turns out you can actually turn on chemical reactions that just didn't happen before.
Okay.
And you can really accelerate your chemistry. So to these, very often we try to get these quantitative conversions. Now, this liquid assisted grinding, the question is, how does it work? And that's the big question of this area of mechanochemistry right now. And why am I telling you this is because what we looked at, maybe I think last year, we started doing some of these in situ measurements on chemical reactions that release water. So again, it's a chemical reaction, water is released, but so the final product is both your product and a little bit of water released. But we were actually able to look at these reactions mechanistically and see that this small amount of water being released actually acts as a catalyst. So then we went on to design the same system to actually use, if you wish, a small amount of an additive that would generate a liquid and then sort of catalyze the reaction.
Okay.
I'm not sure if I'm answering that. But the other thing is you could have reactions in which, let's say, water is released, and that water can then form a part of the final product, if you wish. Form a solid hydrate, for example.
Yeah. Interesting.
So that's definitely possible. Yeah.
Okay. So how much control can you actually exert on the chemical reaction? Can you? And this was another one of my questions. And I was thinking people do reactions where they deposit, say a monolayer of one material on another one. Is it possible to do something like that, or is this more for a larger scale of a reaction?
Right. So this can be done in very small scales, and mechanochemistry is also a very wide area, and so you do have people out there who actually do mechanochemistry by scratching surfaces, right? And just induce new chemical species on the surface by sort of AFM scratching or nano scratching. So depending on what device you're using, you can either create layers, patterns, or you can just grind it all up on a ton scale. I know it sounds very different, these things, and that's one of the current interests. I'm not going to say challenges, because I think we are past the challenge
Hmm.
uh, situation now. It's really a big interest in how do we bring together all these different types of mechanochemistry under the same roof.
Yeah. Okay.
Yeah.
Yeah, it's a fascinating field. As Isaiah gave us some insight into it now, and you've just kind of blown it open as to what is possible. Okay, so our next question here is from actually Dr. Kyle Grice, and he wants to know if there's a way to model. You kind of touched on this a little bit. Is there a way to model mechanochemistry using computational chemistry?
Wow. Yes, absolutely, Kyle. That's a great question. This is something that we are definitely very much involved in, and not other groups are too. You've seen that we've done some periodic DFT and also with Mihail's as a way to try to start explaining the thermodynamics behind mechanochemistry.
Hmm.
But we are very actively working on using, for example, molecular dynamics to understand what's happening when solids encounter and mix. And the next steps from that at some point are going to be, well, how does the reaction really take place? I would like to say that we are the first ones doing it, but we are not. And a pioneering paper on that, if you're interested, is actually published by Michael Ferguson, working again with Stuart James in the UK. They published a really daring chemical science paper, I think last year, using molecular dynamics to understand the mixing of organic crystals colliding. So the answer is yes. This is a really very nascent area,
Hmm.
but with a lot of eyes kind of turned towards chemistry these days, I have a feeling it's going to be moving terribly quickly. As I said, we are starting to look at it a little bit.
Very cool. I think Michael actually joined our Discord, so he and Kyle have been
Yeah,
talking
I was
already a
going to
little bit.
say that we are actually unbelievably lucky to have Michael on board of our team now. So Michael has now, despite all the COVID limitations, has managed to find his way to Canada, and he actually just came last month.
That's awesome.
He just recently came out of self isolation, and he's we are looking forward to pushing forward our computational abilities.
Yeah, that's fantastic. All right, this is a selfish question, but I'm curious based on what you showed whether or not this is a possibility. So I've done some work on metal oxynitrides, and specifically a solid state, basically a solid state reaction to form metal oxynitrides. Now they're of interest for like water splitting and things like that, but traditionally you have to do a two-step high temperature reaction where in the first step you make the mixed metal oxide, the second step you flow ammonia in a tube reactor and swap out some of the oxygen for nitrogen. And the work that I had done was a solid state reaction where you basically take the nitrate precursors with urea, react them at about 500 degrees C, and you get the oxynitride that way. And it was much shorter time. Obviously, you don't have to mess with ammonia and all that. All of that to say, could you use mechanochemistry to induce that same formation without even having to heat it up to, say, 500 degrees C?
Well, Ben, you probably noticed that I'm the sort of guy that just says yes. So I would say why not? One just needs to figure out exactly what one is doing.
Hmm.
Obviously, depending on how one performs the mechanochemistry, grinding or milling or some other type of mechanochemistry, there may be heat involved. So you can actually deliberately introduce heat
Hmm.
by choosing the right milling equipment. Something that's an interesting possibility is there is more and more of these heated mills these days. So maybe you can do ball milling and perform your thermal reaction not at 500 but maybe at 250, which
Hmm.
could be interesting. I would say why not, and why not give it a try. There is some really fascinating inorganic mechanochemistry that we haven't done, but I know of people reacting nitrogen gas with metals and
Hmm.
people doping titania with nitrogen by milling at room temperature. So I think there is a lot of opportunities to figure out. Uh, one thing maybe that's a bit problematic is people try to grind something, then nothing happens. They say, well, that's it.
Yeah.
The point is really to be, I like to say, unorthodox. You try to mill this way and that way. And instead of saying, I'm going to now bash this reaction until it does what I want, I say, let's try to cheat a little bit, right? So, sprinkle a little bit of liquid in there or something, see what happens.
Yeah.
And it turns out when you kind of have this liberty to do these kind of more funky, people would say, you're not maybe a chemist, you're behaving more like some kind of engineer. You're just adding things to see what happens, maybe.
Yeah.
It works. This system grinding, just bloody hell, it worked all over the place. And we are also finding out we can activate metal oxides by adding like a bit of ammonium salt. And then you look at it, it turns out there is some really interesting protic chemistry catalysis going on. But I would say why not? And milling, grinding, maybe by heating, maybe with an additive. But the chances are you're probably going to discover something even better than you wanted to do.
Hey, that'd be great. We'll have to talk. Let's see what we got here. Okay, so this is from Isaiah. When making pharmaceuticals mechanochemically, do you have to worry about purifying by normal methods such as columns, which require large amounts of solvent, or are the reactions largely cleaner?
Can you say that again?
Yeah, absolutely. Sorry, that was a long one. So when you're making pharmaceuticals mechanochemically, do you have to purify them by normal methods like with columns that require large amounts of solvent, or are the reactions themselves largely cleaner?
I think the gloves are off now.
Yeah, yeah. I told him it was a chance to ask you hard questions.
If I said, oh yeah, this is clean stuff, I would obviously be lying, right? That's not. Pharmaceuticals are, pharmaceuticals need to be clean, and you need to make sure there are not micro contaminations and so on. So definitely, and you've seen some of the examples that we had of making drug molecules, metal catalysis. So it's kind of painstaking to actually get the metal catalyst out. We try to simplify it. For example, we remove the metal catalyst by milling. After the reaction is done, we do one more mill very briefly with aqueous sodium EDTA, which actually picks up very efficiently the copper catalyst out.
Yeah.
And then you just kind of wash it away with water. So we kind of need to wash it away with water. But generally after that, we find these samples come out as very nice white crystalline solids, microcrystalline. We haven't done micro elemental analysis. We should. But it's not like we have major problems with contamination.
Yeah.
So definitely, when making drugs and pharmaceuticals, I'm sure that one will always have to do some kind of purification procedure, because simply these are things that are being delivered to humans, animals, and so on.
Absolutely.
But it's not critical, and in a way, it's a good thing. I would say, maybe I can kind of sell the idea here a bit more. Is you can actually reduce the amount of catalyst significantly. We find in some cases that reactions, catalytic reactions, which are not very efficient in solution, or maybe don't really take place at all, they happen very, very quickly, very easily by milling. And my explanation for that is very simple. If you have 5% catalyst in solution, you don't have 5% catalyst. You have 5% catalyst with respect to your reactants, but towards the entire composition, the fraction of your catalyst is maybe 0.005%.
True.
Solvent, everything. But when you actually do a milling reaction, you have your A, you have your B, you have your catalyst. So your 5% catalyst really is that 5% catalyst. So catalyst overall, I believe generally should be much more active. So to make the long story short, we find we can actually reduce the amount of catalyst for chemistry. We've been looking at that recently with the olefin metathesis, using really traces of catalyst at this point. And also people like, I don't need to mention again, people like James Mack have shown you can actually use just the surface of the milling device, the surface of the milling ball. If it's made from the right material, you can use that surface as a catalyst.
That's very cool.
And again, maybe that's what we should be doing, because it looks like that way you may not be even getting much or maybe any leaching from the milling equipment.
That's a good point. Yeah, I mean, if it's a solid material, it's not going to that doesn't chip off or anything, then yeah, absolutely.
Right. I mean, people have the Mac group looked at some of these things. They used, copper-based balls or silver foil to do catalysis. And from what I understand, what they see is that if you weigh the milling device before and after catalysis, you hardly see any difference in weight. So it looks like it's not really the metal rubbing off, but it's happening right there on the surface.
That's very cool.
Which is kind of cool, yeah.
Yeah.
I'm jealous. I'm terribly jealous.
Yeah, that's really neat. Let's see. We've got Dr. Fayer Ho here. She wants to know if you have different structures that can be formed using the same starting material, so like different polymorphs. How do you make sure that the mechanochemistry synthesis forms one of the polymorphs and not the others?
Oh, that's a great question. Thank you, Fayer. I appreciate that a lot. That's a lot of interest is in that, in like pharmaceuticals, organic molecules, organic polymorphs. And that's where the idea of adding a small amount of liquid is really important. And this is very poorly understood. This is where we need modeling. And some people, like, for example, Aurora Cruz Cabeza, have been doing some really nice calculations. But overall, the systems are really very poorly understood. But adding a small amount of a liquid phase can actually cause the transformation of one polymorphic form into another by milling. I must also promote some people in my group. We have a really, really talented postdoc, Lucia German, who has actually shown recently that, at least in some cases, you can control with impact. So, whether you use heavier milling balls or different frequency or different material from which the milling jar is made. So you use materials which have maybe different Young's moduli, right, and so on. You can actually control which polymer forms. So I wish I had it included in slides, because that's something that's very much exciting us right now. The fact that you can, grind softer or grind harder, and you can actually push the polymorphism of your product one way or another. And Fayer, this is a really good question, because I think I actually have an extra slide here. Hold on.
Yeah, absolutely.
Oh, check it out. I actually didn't want to show this at all, but here's an example. This is not organic polymorphs. This is MOFs. This is some work we've done a couple of years ago, where we tried to actually predict which MOF structure we will get for this system, which was previously not really characterized. And well, predictions worked perfectly. That's all I'm going to say. But the important thing is this MOF exists in two polymorphs. One of them has a quartz structure, and this one has a sodalite structure. And it turns out that if you just grind carelessly, you're going to get this quartz material, which is more stable. But if you grind gently and you add, let's say, a liquid phase during your milling that can occupy the pores of the MOF, you can actually stabilize this open framework structure. And the difference between them is measured, again, thanks to the Navrotsky team, roughly 16 kilojoules per mole. So again, by controlling the reaction conditions, and this was done deliberately, this was not an accident, because we looked at the reaction, we realized there was an intermediate form that we need to somehow stop the reaction that's at that level. And then, the person who did the work, again, our postdoc Thanasis, he said, well, I'm going to grind softer. I'm going to use materials which have lesser Young's moduli than, for example, steel. So he switched on to Teflon milling jars, which are softer and gentler, and milled at a lower frequency, went down maybe to 25 hertz, and then added the liquid that can occupy the pores. So with all these measures applied, you can actually isolate these less stable open framework materials. I know it sounds a little bit like magic, but it's becoming less and less like that, because we know now if you want to mill harsh, you're going to get one thing. If you want to mill softer, you can get something else. And then if you're milling softer and if you add different additives, you can push the reactions, to do different things. So Fayer, I hope this helps. I can obviously answer more questions if you wish by Twitter, no worries. But just to make maybe a quick conclusion, there is a bunch of ways through which polymorphism can be controlled, both for framework materials and molecular materials, addition of liquids, addition of maybe catalysts, changing the milling device, changing the milling assembly, changing from harder to softer materials. So,
That's really cool. Let's see. Okay, so Isaiah wants to know: can you use different forms of mechanochemistry to control regio selectivity or stereo selectivity?
Yeah, so see, that's one of those questions where I always say yes, absolutely. Well, I would say each flavor of mechanochemistry, whether it's ball milling or maybe in a shaker mill or maybe using a planter mill, whether it's screw extrusion or acoustic mixing or any other method. Speed mixing, I understand, is a very popular thing these days. So rapid spinning, right?
Mm-hmm.
I believe each of these methods has a different way of delivering the mechanical energy and mixing the particles,
Mm-hmm.
and that all leads to different chemical behavior. So how that's going to happen? How are we going to connect the mechanical properties of our system? So
Mm-hmm.
the choice of instrument, the choice of motion, the choice of grinding media, the stuff that does actually the grinding. How does that kind of physical design of the device and I guess it's kinematics or something, right? How does that
Yeah.
actually translate to different chemistry? Now that's an excellent question. That's that $1 billion question, right? So
Yeah.
so I think whoever figures out how they can relate the physical design of a milling instrument to how it affects chemistry is
Mm-hmm.
probably going to do really well. And maybe a few years ago I would say it's very difficult, but I think it's becoming more and more likely it's going to happen in the next 5 to 6 years that there's going to be papers on that. People are starting to do a lot of really complex simulations, and now with these methods of actually monitoring reactions in real time, looking at kinetics, one can actually start to make the direct connection between the choice of milling apparatus, reaction kinetics. And I think at that point, you know, understanding how chemical selectivity is affected
Mm-hmm.
becomes only one more step away. So to answer Isaiah, I'm sure there is an effect, and but right now it's unpredictable, but it's not going to be like that for long.
That's a great answer.
And maybe I'm over enthusiastic.
No, honestly, I like the enthusiasm. That's fantastic. Let's see. Kyle would like to know: is okay? Okay, this is a good one. Is there a way of monitoring heat and pressure during the mechanochemical synthesis?
Absolutely. And the truth is, when I tell people, wow, we looked at in situ reactions, all that stuff. Um, the truth is that before people started looking at in situ diffraction and spectroscopy, people looked in real time in the changes in the pressure inside the milling jar.
Hmm.
So again, this is not a direct measurement of what is happening in the jar. It's sort of a related thing, a generated gas, but
Mm-hmm.
people have been looking at that. People have also been sticking thermocouples into milling jars and observing the thermal effect. So kind of, indirect observation of chemistry.
Mm-hmm.
So people have looked at that, but you may be asking about a different type of pressure. Are you thinking about the pressure of, evolved gas or absorbed gas during milling? Or maybe are you thinking about the pressure that is actually being exerted upon the material that's being milled, during collisions, impacts, and so on?
Mm-hmm.
Um, that I don't think has ever been measured, and
Okay.
that would be really interesting to observe or calculate.
Yeah, that would be very
I hope
interesting.
this helps.
Yeah, I think that's a good answer. Yeah, Kyle says pressure exerted for sure.
Yeah. Well, again, self promotion is limitless. So we actually did publish a paper. The first author is Ivana Brekalo, who was a joint student between our group and Travis Holman at Georgetown. And there was a chemical science paper that she pushed through on actually measuring CO2 pressure during mechanochemical synthesis of MOFs from metal carbonate. And that was actually
Ah.
I think it was cool work. So check it out.
Yeah, that's
If you're
very cool.
interested, I can send it over.
Yeah, absolutely. All right. Okay. Yeah, this is a question I had. So, in one of your slides, you talked about using zinc oxide as a precursor material. What's the mechanism by which you actually are able to dissociate the zinc from its oxygen?
Right. So here is a maybe it's good to have a slide open, huh? Slides are always helpful. So sec. Right on. So this kind of reaction,
Yeah.
and we use this for a bunch of other materials. So like we were making pepto-bismuth from bismuth oxide. That was fun. But
Nice.
Overall, these reactions, we find out, I think of them as classical acid-base reactions. Acid plus a base like the oxide gives you water. That's what happens. How it works in detail, well, we have some evidence that protic catalysis here is very important. So,
Yeah.
and we don't have any direct evidence for that. I would not be surprised if it turns out that people have measured something like this, but in a very different field. So I'm not aware of it. But we believe what's going on, that there is actual partial protonation happening on the surface of the metal oxide,
Mm-hmm.
and then that enables the sort of opening of the surface, attachment of the imidazole group, and then eventually the oxide splits away as water.
Okay.
So I believe that motion of protons around hydronium ions on the surface is quite important. What evidence do I have? It's very, it's not direct evidence. We have observed some species which we managed to crystallize.
Mm-hmm.
But yeah.
I mean, yeah, it's an educated answer for sure.
It's an educated guess, and how I tell people in my group, I say usually if it's my guess, it's probably wrong. So.
Hey, there's nothing wrong with that.
Yeah, there's definitely some protic catalysis going on there.
Okay.
But details we do not know.
Okay. Faye, I also wanted to ask. So this was she actually asked this right before you started showing the XRD work that you did. So maybe you can kind of expand on that a little bit. She was wondering, is there a way to study how the mechanical synthesis works, and can you follow the structural changes in the chemical reactions that happen during the synthesis? And so, like I said, the XRD you showed, you can follow at least the crystalline structures. Is there anything else in addition to that, or?
Yeah, there is a ton of things, and I made the cardinal mistake of not having my whole deck of supplementary slides. One can do tremendous amount of things without a synchrotron. Synchrotrons are a bit clumsy. They happen to need like a huge electrical power plant or a nuclear reactor.
Mm-hmm.
So it's not necessarily something you can have at home, but you can actually do Raman spectroscopy. So we worked with a team initially in Zagreb, Croatia, and now a lot of other people are doing it too. You can actually just get your normal, usual, fiber optics Raman probe,
mm-hmm.
stick it next to the milling jar as long as it's made of a transparent material, and measure the spectra. It's great. And you can see a lot. So maybe I should just highlight here. I didn't stress maybe enough is this movie I've shown. This movie that's been taken by Michael Brand. Really, the cool thing about it, well, it was maybe 10 years ago that we first started doing this, is the use of a transparent plastic jar.
Mm-hmm.
So again, we have not really been trained in mechanochemistry. So when we started doing this chemistry 10 years ago, it was all steel equipment and tungsten carbide,
mm-hmm.
heavy materials for grinding and milling. And actually, when we were preparing to do those synchrotron experiments, that was amazing. Somehow we managed to get, some in-house beam time, and we were given permission to bring this ball mill, into Grenoble and stick it in front of this extremely expensive X-ray detector and so on. So we were like freaking out what's going on, and the time at the synchrotron is terribly expensive, so we don't want to waste it.
Oh yeah.
So we really freaked out, and I said, well, maybe these X-rays are really going to go through steel, but maybe they don't. And then we are kind of, you get a problem.
Yeah.
So we ended up making these milling jars from polymethyl methacrylate, PMMA, which is what they call plexiglass, right?
Yeah.
And we realized it actually works. Not only that these beautifully open, snap on, snap off, but they're also transparent. And we realized that it's actually so easy to see what's happening in there. Yeah. So honestly, if you ask me what was for us maybe for our little group a important innovation, was the fact that we realized we can use cheap transparent plastic to make milling jars. And And that really helped in doing measurements at the synchrotron. But it turned out actually we didn't have to worry, because that synchrotron beam, that thing went through 3 millimeters of steel coming in and coming out. So no problem.
Yeah.
But these are pretty cool. You can actually observe stuff. Now, why am I talking about this? Because these transparent jars, they're fantastic also for Raman spectroscopy. And our former student, Patrick Julian, working with another former student, Chris Nichols, they actually figured out how to make these jar-like devices from sapphire. And it sounds pretty fancy, cool, but it was really easy. These fellas managed to put together, rig something up, and there were these sapphire milling jars, which are fantastic because they have really, really low background when you're looking at organic reactions. So anyway, to make the long story short, I didn't tell you I always babble too much.
These are great.
You can look at mechanochemistry either by diffraction, synchrotron, X-rays. You can do Raman spectroscopy. You can do anything, really. You just need to kind of plug the right instrument next to it. It's terribly simple. There was a really nice report recently from the Emmerling group in Germany, in Berlin. They actually used in situ X-ray scattering EXAFS methods to follow the formation of gold nanoparticles. So that's something really cool, right? So
that's very cool.
I really think you just need to have the right people and the right interest on board, and everything can be done.
Yeah, that's incredible. That really is. Let's see. So what do you see? This is from Aurorigans. What do you see as a high priority area of industry that could see a lot of benefit from the adoption of mechanochemistry in the near future?
Really, really good question. So we really like to do things that are as applied as possible. And I find this very difficult to pinpoint as a priority. I can tell you that we had, and other groups also had, a lot of interest from 3 or 4 fields. A really big one is pharmaceuticals, because mechanochemistry, being able to make molecules by milling, solvent-free. So, it's even better, I understand from people in the field, it's even better than recycling solvents, because recycling pharmaceutical solvents costs a lot in many ways. Sure. And here, if you can just make things without using those solvents, or at least eliminating some of that solvent, is terribly, terribly, terribly important. So there is definitely, I would say, pharmaceutical synthesis and manufacture. We also had some contacts with people who are trying to look at how they can combine mining, mineral processing with chemistry, so that you actually do processing of minerals chemically while already in the first step of particle size reduction by grinding ores. So there are some people who are interested in that. So I think that would be extremely interesting, and I think that would be extremely beneficial, because it will use the existing equipment that exists in mining, which are many, many ton scale mills.
Yeah.
And actually combine them with existing chemical reactions. In that way, reducing the number of steps. So that's one important area of application, I would say.
Yeah, absolutely.
And we also had some interest recently in again biomass degradation and actually plastics depolymerization.
Oh, no, that would be an interesting use.
I would say plastics, mining, and the pharmaceuticals are probably the tops.
Yeah, the plastics would be a fascinating one. That's a big issue right now.
Yeah, we actually have some really nice results with that. We hopefully to publish them soon with the Eclair group, combining enzymes and the plastics.
Oh, that'd be great. We'll have to get you back.
or bring Karine on board.
Absolutely.
Absolutely.
Let's see. Okay, so Isaiah had another good question for you. For the Botopi stuff, is there some pore size control through the liquid assisted method that could be observed? He suggests maybe more or less dye trapped through displacement of the solvent molecules.
I'm not quite sure I follow that. Can you say that again? Sorry.
I forget. Isaiah, can you, what's the LAG stand for again?
Liquid assisted grinding, yeah.
Yeah, that one. Okay, so is there pore size control through liquid assisted grinding that could be observed For instance, maybe more or less dye being trapped through displacement of the liquid-assisted grinding solvent molecules.
So once one performs the liquid-assisted grinding to synthesize MOFs and porous materials, those liquid molecules, they get trapped in there, in the material, for sure. So as you're milling on, your system becomes actually drier and drier and drier. And eventually those molecules, once the material is made, eventually need to be evaporated and removed out.
Okay. So Isaiah also wanted just to say thanks for the shout out, and that he appreciates the opportunity and is glad to have met you and worked with you, and is very proud of the work that you guys did together, which as an outside observer, I agree, it was awesome work.
Well, Isaiah knows it ain't over yet, so we still got the ton of unpublished stuff, which we're going to get out slowly but surely.
Oh, that's awesome. Okay. Let's see. Oh, okay. Oh, this is a good question from Fayer as well. How did you actually mount the sample into the beam line? Because if she understands it correctly, the reactants are shaken constantly. So how do you mount it such that it's being shaken constantly in the beam line? And do you actually like place the ball mill directly in there, or is there some other trick that you use?
Yeah, well, hold on, let me show you. Here's the actual setup right there. Give me a sec.
Mm-hmm.
So here it is. So this is really the first set we used. This was in Grenoble. So let me just show you this. So this here, that is the actual ball mill.
Okay.
And we have modified the ball mill so that this thing here, which is the sample holder, which is positioned normally here, sticks up. So that from this little yellow spot here behind, that's actually a tube from which, a collimating tube from which the X-rays are coming. So the X-rays go from here through the jar, which is just, shaking left and right.
Yeah.
And then maybe 3 or 4 meters behind where I am now, so where the viewer is a detector that measures the diffracted beams.
Got it.
This is kind of looking from the side. This is the ball mill.
Yep.
I think the detector is somewhere around here, maybe.
Mm-hmm.
Yeah. And the X-rays are coming through here, through this collimating tube here. Yeah.
Yeah. Okay.
No, not this one there. Sorry, this one here. Yeah.
Yeah.
So that's pretty much how it's designed. And so the ball mill is placed on an XYZ holder that kind of allows you to center it, and you kind of place the sample so that the X-ray beam is passing roughly through the center jar a little bit towards the bottom, so that there is always some sample in there, because obviously the amount of sample in the beam varies with time as the things are moving.
Mm-hmm.
So one problem with this method is sometimes the sample gets sticky and gets stuck to the actual milling jar.
Yeah.
And you see your signal slowly being lost, and then you say, "Oh my God, I'm milling my material until it loses crystallinity. It's becoming amorphous," and it's not really what it's doing. It's just simply getting stuck to the walls and not being exposed to the beam.
Okay. All right. That makes sense.
Actually, so if there is interest in that, this is the first paper on this, 2013.
Mm-hmm.
The supplementary information for this paper contains a lot of data on the experiment design.
Okay.
And we also then published later on a protocols paper that actually describes this step by step.
Oh, nice. Okay.
Yeah. So I mean, the whole idea here is this was a new method, and we really wanted to make sure that whoever opens this paper can actually do it, as long as they have an X-ray beam in hand and a synchrotron.
Yeah.
Everything else should be easily doable, right?
That's fantastic. There's a lot of papers that don't bother to do that, so that's very much appreciated.
Well, the way we think is, science is really for everybody. So, hey, everybody have fun, right?
As it should be, yeah. Let's see. So, somebody in chat, the Warden009 wanted to know if the synchrotron provided any information beyond the kinetic curves.
Beyond.
The kinetic curves, like, or the
Oh,
changes
yeah.
in the
Sorry,
phase
sorry.
over time.
Right. So well, kinetic curves are really a huge benefit, but what we were able to also see is, in some cases you're actually able to do quantitative measurements. So you can put a diffraction standard in there, and,
Hmm.
and now you can actually do quantitative real-time analysis of what's going on in there. And excuse me, and you're starting to see that the composition of your milling mixture, if you're observing it in real time, is
Hmm.
very different than what you do by stopping the reaction, sampling it out, and measuring, and so on.
Yeah.
So, for example, we see the appearance of phases that you normally you don't observe because they last maybe only a few minutes.
Hmm.
So now you know that they're there. We also have observed, I was very shocked by this, we have observed that in some cases, roughly 30 or 40% of the reaction mixture is amorphous. Uh,
Hmm.
Compare that to the actual doing milling, taking the sample out and measuring separately. In
Yeah.
such an experiment, we see maybe up to 5 or 6% amorphous phase. So this tells us that during milling there is a lot of amorphous non-crystalline, I like to call it active phase in there.
Yeah.
And the moment your milling stops, it looks like this phase just relaxes so quickly by crystallization, you don't know it was there. So we are seeing some this
Huh.
interesting new mechanistic insight. So it's not only just the kinetics, but the composition of the mixture that we are elucidating.
That's really cool. So okay, this goes to you to the last part of your talk where you were showing the reaction with an oxidant. And somebody, this is I can't take credit for the question because somebody brought it up in chat. But what would happen, or what do you expect would happen in a nitrogen atmosphere, um, with that reaction?
Oh well, actually, we did that. You're talking about the hypergolic
That's
systems.
it. Yeah.
Yeah, my favorite movie. Yeah, so we actually done that, and I don't remember if we included a statement on that in the first paper, but we definitely see ignition, and
Okay.
because at least some of the ignition comes from the oxidant touching the material,
Hmm.
and that leads to that ignition there. But it
Yeah.
doesn't last long, right? Because you don't have air to support further burning.
Okay. So you still achieve the ignition. It's just
Yeah,
much less colorful, I guess.
yeah, it's not terribly exciting, but it happens, and that is really important,
Oh
right?
yeah, absolutely. That's impressive that it can still happen.
Except I don't think we did nitrogen. I think we probably did it with argon. It's easier to actually because
Makes
argon
sense.
flows down, right?
Yeah. Oh yeah. Argon's a whole lot easier to work with for that.
Yeah.
Um,
And
Isaiah, I want to know: is there anywhere that you can suggest to buy milling jars made of different materials?
um, a way to justify, you said, or
A place to buy them.
oh yeah, absolutely. I mean, the classical, uh, classical suppliers of milling equipment like Rich or Fritsch or Netsch. These are all interesting names, by the way.
Yeah.
Um, yeah, they're very much like Friscic, right? Yeah, I think there is standard one can buy steel, alumina, agates, zirconia, tungsten carbide. Um, the other thing is also, so my former student Chris Nichols actually started up a company
Hmm.
of his own that actually makes different milling jars.
Oh.
So he actually came up with this design he calls smart snap jars, and I think he makes them or gets them manufactured from zirconia. I think there is also plastics,
Hmm.
uh, Teflon, steel, tungsten, such things. Yeah.
Yeah.
But normally, honestly, well, for non-standard things, what we usually do is we try to get a machine shop and to make one. Yeah.
Okay. Nice.
As long as it's metals, it should be fairly easy to make. Ceramics a little bit more and more difficult, but
Yeah, I could see where the ceramics would be a more difficult thing to work with, at least in terms of in terms of making the jars.
right. But also, there's so many of these online services now that you can simply send people your design. And
Hmm.
by the way, again, the protocols paper I mentioned, in that there is actually a AutoCAD, I think, design for milling jar. So if
Wow.
you want to make your own, it's there with the measurements. So you can send it to your machining service or your online supplier of ceramics,
Yeah.
you can maybe try to 3D print it yourself. I think there's been a couple of papers recently with people who have been actually 3D printing jars.
That's fantastic. That's very cool.
It's pretty cool.
That's awesome. So the last thing we have here is just another comment from Isaiah saying that he just wants to say it again, that you're awesome. It was a great talk. I agree. And he wants to thank you for being both a great mentor and a great friend.
Hey, Isaiah, come on, you're making me emotional here. Thank you very much.
Yeah.
I love you.
Yeah, this, like I said, this was fantastic. This, I knew it was going to be a good talk, but man.
I hope it hasn't been too bored and too tiring. I mean, there's a lot to say. And, it's such a big area. There's so many good things going on, and everything is a little bit exciting,
That was the most interesting part, because, like I said, Isaiah sort of, I was aware of ball milling and things like that, but I wasn't really aware of what you could do with it aside from breaking a powder down or something like that. I had no idea you could do a reaction, and now here you are laying out all these different possibilities for it, and it's just that's amazing.
Well, I'll just simply say, as I told you, I'm terribly enthusiastic. So the answer is always yes. Why would it not be possible?
Yeah.
It all depends on the amount of time and will one puts into this. And it sounds a little bit like megalomania, I know. But I really am thinking, why wouldn't we think about translating our industries, our manufacturing into a solvent-free environment? Maybe it does not need to be mechanochemistry, maybe something else.
Yeah.
But do we really need all these solvents? I think that's the critical question.
I think it's a good one to ask.
I'm not convinced that we do.
Yeah, I mean, I'd say you made a pretty good case. Well, I'll give the chat a last chance to ask any final questions, but I suspect we've gone through all of them. So I will say thank you, first of all, obviously, to Tomislav for coming out. Like I said, fantastic talk, just highly informative, very entertaining, just wonderful. And thank you as well to everybody that came out, to all the people who asked questions. There were some really fantastic questions asked. And let's see, next week we'll be off for Thanksgiving, and then we will hopefully be back the week after that with yet another talk. And for everybody that was new that came out, thank you. If you would like to present, feel free to get in touch with me. We'd be happy to have you on. And I guess with that, I will say have a great weekend, everyone. Please stay safe. Wear a mask. And we will see you next time. Thanks again, everybody, for coming out.
And happy Thanksgiving again. Thanks all.